galaxies over here that are full of stars and gas and so on. So how did we go from here, nearly perfectly homogeneous, to here, completely inhomogeneous? And the answer is very simple, it turns out. The answer is simply gravity. Gravity is an attractive force for matter. You know, when you throw this thing up, it falls. So, regions over here which are rare, which are slightly overdense compared to the background, they will have slightly higher density in the background. Therefore, they will have a slightly higher gravitational attraction than the background, because of which particles from around them will fall towards them. Therefore, those regions will become more overdense. Therefore, the gravitational field increases. Therefore, they attract more particles and they become more overdense. And they become more overdense. And they become more overdense until finally, underdense regions have lower gravity. So they attract their matter less. So matter flows from underdense regions into overdense regions. And these overdensities, these tiny overdensities, these things over here, they grow with time very slowly. But remember, the universe is really old. You have time. They grow with time, and these tiny overdensities become today's galaxies and clusters and superclusters. So all that's happening is that you have these small inhomogeneities, and they just, by gravity, they grow with time. That's all. And that's the reason that there was a prediction that you must have anisotropies or inhomogeneities. If you did not have those inhomogeneities, you could not grow structure. You can't form galaxies. You must have these inhomogeneities to form these galaxies. So that's the picture that we have today for galaxy formation. So let's look at a movie of this. So this is a picture of the formation of galaxies starting from a redshift of about 20 to today's epoch. So just look at this. Pink over here is overdensity, blue is underdensity. So blue regions are empty, pink regions are full. And you can see that matter is flowing from these blue regions into this region over here. That's redshift 0.1, and that's today. So this is the Millennium simulation by Volker Sprinkle and at NPRA. Let's look at this again. We start at redshifts of 20, and the universe is quite uniform still. Now you can see blackish things happening, redshifts of 10 or so, bluish, it gets bluer now. And now you start to see these filaments, these thin arms. And matter is flowing along these filaments, away from these voids into the filaments, and then flowing along the filaments into these central regions. And it's these central regions that are the centers of gigantic galaxies, superclusters of galaxies. Let me emphasize, this is 50 megaparsec. This size over here is 50 megaparsec. A galaxy is about 30 to 50 kiloparsec. So this size is 1,000 times bigger than a galaxy. So galaxies are points over here. They're tiny little points. In fact, even a thing like this is a supercluster. This is a massive, massive supercluster. But you see another prediction. If you look outside in the universe, you should see structure in these filaments. You should actually see matter form, galaxies forming in lines along, with matter falling along this. So let's look at this again. So we start at redshifts of 20, and it's quite uniform. And just look at one part of the graph, here or here, and look at what happens. So now you see the first voids, the first big voids are forming. This is the redshifts of 5. So by redshifts of 5, you already have lots of galaxies that are formed in the universe. By redshifts of 2, there are hundreds and thousands of galaxies around, millions in fact. And it gets more and more and more filamentary with time. So when you look at galaxies in the universe at redshifts of 1 or 2, you expect to see these filamentary structures. And the wonderful thing is that somewhere in the early 80s, 1980s, the first big galaxy surveys were done, the CFA surveys, and they actually found exactly this. They found these beautiful stripes, these filaments in redshift space. So you measure the redshifts of all these galaxies, and you find that all the galaxies in some direction are in a line. They all have similar redshifts, and they're all sitting in a line. And that was done before these simulations. And this is exactly what you see in the real universe. So let's zoom in now on this big region, just to give you a feeling for what a cluster looks like. So that's now 1 gigaparsec, huge. And now you're going into the box. So you're going closer and closer to a galaxy. And this thing now becomes 500 megaparsec. You're going closer and closer to this galaxy. So now this thing becomes 250 megaparsec, and now you see this thing has structure inside over here. And as you go to smaller and smaller scales, you see more and more of these filaments coming in. You can see these thin, narrow filaments coming out. There are a gigantic cluster here, 62 megaparsecs, with a smaller cluster here, another cluster here, 30 megaparsecs. Again, huge, much bigger than our galaxy, 1,000 times bigger. 15 megaparsecs. You can see a huge object now in the middle over here, and all of these are galaxies. 8 megaparsecs. 4 megaparsecs. And sadly, that's where we stop. And now we go backwards, but you see the pattern that you saw at 4 megaparsecs of these filaments and voids is exactly the pattern that you see on big scales. There's some self-similarity in the pattern. Let's go back and look at this again. Remember, 8 megaparsecs is about the distance from us to the Virgo cluster, the Virgo supercluster, which is a gigantic cluster of galaxies towards which the Milky Way and Andromeda and our group are falling. So that's about the scale that you see right at the end. So we are all falling, the whole Milky Way and Andromeda and the Magellanic Clouds are all falling in the direction of the Virgo cluster, which is about 8 megaparsecs away. So that's 62 megaparsecs. That's still much bigger than the scale of even the distance to Virgo. It's 30 megaparsecs. Right at the end, you'll see something which is the size of the distance to Virgo. So that's 15 and a half megaparsecs. This is about 8 megaparsecs. Our distance to Virgo, so we are like something over here, and that would be Virgo. So this is a gigantic cluster of galaxies sitting in the middle over here. And all around it, there are these tiny galaxies that are falling into it on very slow timescales of billions of years. But that is our picture of how structure forms in the universe by gravitational clustering. Okay, maybe you should do it. Do you want to control this?
就解释一下，这是用电脑算的，这是在这个跨千禧年的时候做了一个很远的计划，用超级电脑去算。有时候讲起来很好笑，就是说我们现在之所以在这边可以用电脑解释，到了电脑它从很大的尺度，这个叫宇宙的大尺度结构。那实际上观测到的宇宙的分布啊，就是星系构成的星系团，星系团又有一堆一堆的超星系团，就是用这种像海绵一样，都分布在细胞壁。然后中间就有空洞，比较没有星系的地方，它刚刚叫 filament， 就是一条一条的这个组织。那用计算的结果呢，到了最后的那一个尺度，大概就是我们银河系所在的这个群体，跟我们临近的这个超星系团的那个尺度。所以表示说，用刚才看到宇宙刚开始的那一种一点点的密度的不均匀。让它因为万有引力，让密的越密，疏的越疏，让这样子慢慢的反差越来越大呢，可以长到，可以解释目前我们现在宇宙的结果。
So coming back to your question, when do the first stars form? The first stars form somewhere over here, redshifts of 20. The first regions over here that collapse out become galaxies, that's where the first stars form. So somewhere about redshifts of 20 is is when the first stars form, which reionized the universe later. Okay, so now I'm going to move on to the last two topics of this talk, dark matter and dark energy. So to tell you about dark matter, I need to tell you something extra, which is about galaxy rotation curves. It's going to be a jump. But again, go back to the start of the talk, and you remember that we can use the redshifts and blue shifts of spectral lines to work out velocities of galaxies. So I can tell you if a galaxy is moving away from you or towards you just from its spectral lines. Very easy. But now, in addition to that, I can also tell you if a galaxy is rotating. So if a galaxy is rotating, this side is moving towards you, and this side is moving away from you. So if it's rotating fast, this side is moving towards you fast, this side is moving away from you fast. So what you will see is that if you have a spectral line and you map the galaxy, so this is a galaxy, 3 different points shown over here, the galaxy is moving towards you in this direction and away from you. It's like a disc which is rotating like this. Like this. Right? A spectral line coming from here, because this part of the galaxy is moving towards you, the spectral line is blue shifted. It's moved towards the blue. A spectral line over here, from here, is not going to shift. Because remember, the galaxy is rotating around the center, like this. So this point is not moving. So this central part will stay at rest. And this part, because the galaxy is rotating, this part is moving away from you, and so it's redshifted. So I can do now what is called, I can measure the velocity field of the galaxy. I can measure the velocity at every different point in the galaxy and get the velocity field. And that velocity field for the rotating galaxy is called the rotation curve. It's the rotation velocity as a function of radius. The idea is that if this part of the galaxy is rotating faster than this part, this will be shifted more than this. So things over here will emit somewhere in this wavelength. Things over here will emit somewhere in this wavelength. So I can measure the velocity at different points in the galaxy and tell you how does the velocity depend on radius. Very simple. Simple measure. And now if you take a rotating disk galaxy and if I have circular orbits, how does the velocity depend on radius or mass? So that's the usual Kepler's law. The rotation velocity goes like gm upon r raised to half. You're probably familiar with this. That's the same equation that you use, for example, to work out how satellites go around the Earth. So the mass over here, so for example, for a point over here, the mass in this equation is the mass within this radius. And the radius is the distance from the center. Right? So now, when you go further and further away from the center of the galaxy, the mass is not changing very much. Right? As you go further and further out, you're adding less and less mass. Most of the mass is inside the galaxy. And you see in galaxies, that is, even visually, there are more stars and gas in the center of the galaxy and less far away. So there's much more mass in this part of the galaxy, much less mass over here and here. So therefore, what you expect from this very simple equation is that the velocity from this equation, the mass is constant when you come very far out, but the radius is changing. So you expect that the velocity should be proportional to r raised to minus half, 1 upon r raised to half, because g is constant, mass is constant. So you expect that at large radius, the curve of this rotation, the rotation curve, should form like this, like 1 upon square root of r, this equation basically. Because all the mass, most of the mass is inside. You're not adding any more mass. That's the idea. So now I can go and measure this. I should get a rise over here and then a fall. Very simple. If this model is right, then all the mass is in the inside regions. And when you go and measure this, amazingly, yeah, sorry?
It's a little bit too fast.
Okay. Thank you. In fact, Sorry.
Thank you.
Yep. So where shall I start from? Let's start from here again. You get the fact that we can use spectral lines to probe the motion of galaxies, right? So if a galaxy, the whole galaxy is moving away, you will see all the lines redshifted. If the whole galaxy is moving towards you, you see all the lines blue shifted, right? Now if I take a galaxy and it's spinning, it's rotating, this part of the galaxy is moving towards you. This part is moving away from you. So spectral lines from here will be red shifted because they are moving away from you. Spectral lines from here will be blue shifted, right? But the amount by which they are blue shifted or red shifted will depend on the velocity. It will depend on how fast is this object moving. So if gas over here, if it's going at a lower velocity, it will be blue shifted less than gas over here, and this will be blue shifted less than gas over here. So I can measure the velocity as a function of distance from the center in the blue shift, and the velocity is a function of distance from the center in the red shift. And that gives me the rotation curve. So the rotation curve is simply the velocity of the galaxy as a function of distance, right? That's the picture. So now for this I can write an equation relating the velocity to the radius. Now theoretically, if I take a rotating object, I can show just by basic gravity that the rotation velocity should go like gm, m is the mass, g is gravitational constant, divided by r raised to half. Right? That's the usual, that's Kepler's law basically, what are Kepler's laws. Now, if I take a point over here, the r in this equation, so that's the velocity at this point. The r is the distance from here up to the center of the galaxy. The m is the mass in this small region. The mass interior to that point. Okay? Now when I go further out to point A, the r is of course bigger, and the mass is again bigger because now it's the mass within this distance. But remember, in galaxies, most of the mass which you can see, the stars, are in the middle. Most of the mass is here. So as I go from here to here to here to here, the mass is not changing very much beyond some distance. The mass from here to here is not changing very much. Which means that in this equation, as I go further and further away, the mass beyond some distance is almost constant. It's not changing. But the radius is changing. Right? So therefore I expect, when I do the measurement, before I do the measurement, I expect that if the mass is falling with distance and most of the mass is inside, I expect that at large distances, at large r, where all the mass is inside, I expect that the velocity will go, that the mass is constant, g is constant, so the velocity will be equal to gm constant upon r raised to half. So as I keep increasing r, the velocity should drop as I go further and further out. And it should drop by this functional form, r raised to minus half, because all the mass is inside. So that's what you expect. If I plot the rotation velocity versus radius, I expect in the, so this is now the radius of the galaxy going outwards. At very small radii, I expect this will steadily rise, largely because the mass is constantly increasing. It will rise. And then at some point, I expect that it will follow this blue curve over here. I don't expect that it will be flat. I expect that it will fall at large r. So all that's being said over here is that this curve is v proportional to r raised to minus half. So the velocity will fall as the radius increases with this proportionality. And that's just because most of the mass is in the internal regions. Right? Now, it fits my theory over here. But what happens if I see this? The gray curve. Now I'm in trouble. Because all my visible matter, my stars, are in the center. I know this. I can observe that. But yet, this velocity is not falling like I expect. It's going flat. If the velocity is going flat, this means that the velocity is constant. If the velocity is constant, the radius is increasing, the mass has to increase somehow. There has to be some other form of mass which increases with the radius. If I see this curve, I expect to see this curve. If I see this curve, the mass must increase proportional to radius. And that mass is not being observed. So now let's go and see what the actual observations show. What the observations show is this. So each of these are different galaxies. Every name over here is a different galaxy. And you see that you see the same property, that they all rise in the beginning. And you expect that they will fall. You expect to see this behavior. But what you see is that they go flat. Beautifully flat. The only way you can explain this, well, the only way in standard gravity that you can explain this is that the mass is proportional to radius at large r. The m exactly cancels r, because of which the velocity is constant. And what this roughly means is that you must have 5 to 10 times more dark mass than visible mass. You see gas, you see stars. There must be about 5 to 10 times more matter in this dark mass, which you don't see, than you see in stars or gas. And this we have known since the wonderful work of Vera Rubin in the 1960s, and then work by Carl Begemann and company in the 70s and 80s. That rotation curves of galaxies are flat. That implies 5 to 10 times more dark mass than visual mass. So why is this a problem? It's not a problem, actually. For example, Jupiter. Jupiter is a big planet. There could be thousands of Jupiters, billions of Jupiters. So maybe all this dark mass is just Jupiters. What's the problem? The galaxies are full of these, lots of planets. The problem is that, remember I told you a long time ago, this Big Bang nucleosynthesis constrains the baryonic density. Jupiter is made of baryons. I have a strong constraint on the baryonic density from these abundances. I can't increase my baryon density. That's a problem. Because now suddenly, I need 5 to 10 times more of this dark mass. But that dark mass can't be baryons. That's the problem. So I now need to postulate a new particle. And the wonderful thing is that the cosmic microwave background anisotropies, completely independent to this. They also show 5 times more matter than in baryons. So this is one measurement. There's a completely independent measurement which says the same thing. There has to be a second kind of matter which is not protons, electrons and neutrons, but which is non-baryon. We have no evidence of this matter in the lab today, and we're hoping to find some evidence, but it's very hard. So the model today is that non-baryonic dark matter contains about 25% of the total energy density of the universe. And that comes from rotation curves like this and the microwave background. So we believe that about 25% of the universe is made up of this strange form of matter which behaves just like baryonic matter for gravity, but which does not interact with electromagnetic radiation. Its only gravity. It only depends on gravity. And that's not very unfair.
这两张图里面是在讲这个暗物质的啊，暗物质大概是1960年代的时候发现，这边就讲到基本的运动，中间的质量提供了万有引力，万有引力跟提供了向心力的话，就有稳定的轨道。所以一个东西它受到万有引力的东西怎么样运动，是由于中间轨道的质量。详细的我就不说了，当然大家应该都听懂。像我们太阳系的话，因为质量全部集中在太阳，所以我们行星的运动就会是一个像这样子的，随着距离太阳越远，我们的速度就越来越慢。可是呢，可是我们量星系就不一样，我们量星系到了星系已经眼睛看不到的地方了，可是已经没有光线了，可是偶尔还有一颗星或者有一些云气呢，我们量它们的运动，发现它们到很远很远的地方。发光的地方只在这边，已经到不发光的地方了，它的旋转曲线后来是平的，那就表示在这边还有很多的物质是我们看不到。那这边有个很重要的观念，就是说60年代的时候就已经知道说，不发光的物质啊，暗物质啊，是发光物质的5倍。可是后来的观测，我们后来就讲到说，有大霹雳的那个核融合，以及宇宙微波背景辐射，都说有5倍的暗物质，可是大霹雳已经告诉我们，当时大霹雳出现的这些物质的密度会是多少？我们已经能够解释所有这些我们能解释的物质了。我们知道这些电子啊，这些 baryon 的东西，所以就表示这些我们看不到的暗物质一定不是我们所熟悉的这些物质，它们一定存在，因为它们有万有引力，它们影响了这些发光的物质的运动。可是现在我们还不知道它们的性质是什么，所以我们叫它暗物质。
So we have 25% total energy density in non-baryon dark matter. So I'm going to move on now to the last bit of the talk, which is dark energy. Dark energy is much more exciting. Dark matter is kind of boring. We know that there are all kinds of exciting particles that have been found in particle accelerators. And so dark matter is just one more of those particles. Supersymmetric particles could be dark matter. But dark energy is special. Dark energy has no evidence at all in the lab, at all. Nothing like it in the lab. So what is dark energy? The idea of dark energy is very simple. So gravity, as we know gravity, it's attractive. So if I throw this thing up, it falls. It falls because you have the Earth, and the Earth has a mass. And the Earth is attracting this object. So when I throw it up at some velocity, and use a mic, when I throw it up at some velocity, it goes slower and slower and slower up. The velocity goes to 0, and then it falls. It decelerates. Now think of the universe. The universe should be doing the same thing. The universe has been given some kind of a push outwards, and it's expanding. But there's mass inside. This mass is going to be attracting other masses, which means that the universe's expansion should also decelerate. It should go slower and slower and slower with time. Right? Exactly the same as this thing should be thrown up. And that's just because gravity is attractive and you have deceleration because you have to lose some energy in doing work against gravitational force. And that applies to the universe, it applies to balls thrown up, whatever. But what if we were to throw a ball up? If I threw a ball up, and instead of it falling down or going slower, it actually accelerated away. That will be a problem, because that would mean something is giving it extra energy. That can only happen if gravity is not attractive, if gravity is repulsive. And then gravity can push things away. And Einstein realized this wonderfully about 100 years ago, that this can happen bodies made up of very strange constituents. They are constituents, they are kind of bodies that violate what is called the Einstein strong energy condition. So, which is the relation between pressure and density. Normal matter is not affected by this. But there are certain kinds of bodies which violate this condition. We can talk about that in more detail later if you like. The amazing thing is that observations find over the last 20 years that the density of the universe is actually dominated by this constituent. And the way we find this is that we go out and do measurements of distances to galaxies using type 1a supernovae. The supernovae I talked about a long time ago at the start of the talk. You measure distances to these galaxies and you find that the distances are always larger than you expect if the universe did not contain dark energy. The supernovae are fainter than you expect in their redshift. So remember, you have the redshift of the galaxy. From the redshift, with the cosmological model, I can tell you what the distance should be of the galaxy. But now I can independently measure the distance of the galaxy from the type 1a supernova, because that's a standard candle. If I see a supernova and I measure how bright it looks, I know how bright it is. So I can measure its distance. And what you find, amazingly, is that the distances in high redshift galaxies are larger than what you expect based on the relationship between distance and redshift in the standard model, in the original standard model, without dark energy. If you put dark energy in, because the universe is stretching faster, suddenly the distances match. And I'll show you what I mean over here. So what are type 1a supernovae? Type 1a supernovae happen when you have accretion, you have matter flowing from, so you have a star and you have a second star, and the first star has become a white dwarf. Now white dwarfs are special because they have very narrow mass range. So our sun is going to become a white dwarf in long distant future, 5 million years from now. Now, and white dwarfs are sitting happily in this region. Now when matter from this neighboring star falls onto the white dwarfs can only be white dwarfs up to what is called the Chandrasekhar limit, 1.4 times the mass of the sun. If the mass is larger than the Chandrasekhar limit, it blows up. So when you have this accretion from this companion star onto the white dwarf, it explodes out. But because the Chandrasekhar limit is 1.4 solar masses, type 1a supernova, so you have this explosion, which is a supernova, but it's happening at a very narrow mass range, because it happens exactly when you cross the Chandrasekhar mass limit at 1.4 solar masses. So all white dwarfs which produce a type 1a supernova will produce them just when you cross the 1.4 solar masses. Which means that all type 1a supernovae come from an object of almost exactly the same mass, 1.4 solar masses, slightly more than that. Because of that, you have a very narrow progenitor mass range and you have a very narrow type 1a luminosity range. That makes them wonderful standard candles. And that means that you can get the distance to the galaxy. So if a type 1a supernova happens in a very distant galaxy, because you know what the luminosity of the supernova is, you can immediately measure the distance to that galaxy. And that's why they're wonderful. And as I said, in cosmology, the distance to an object is related to the redshift. And the distance redshift relation depends on the cosmological model. It depends on what is there in the universe. If there's more matter and less radiation, you will see one distance redshift relation. If there's much more radiation, much less matter, you'll see a different redshift distance relation. So all you have to do to test cosmology is to measure the distance to the object and its redshift. And then you can directly test the cosmological model. And the wonderful thing about type 1a supernovae is that they are very bright. And today we can detect these type 1a supernovae to redshifts of 2. So you measure the distance to the supernova by using this standard candle approach. You measure the redshift of the host galaxy, and now you know the redshift as the distance as a function of redshift. And test the cosmological model. And that's a plot of the best data today. So this is a plot of the average distance between galaxies relative to today's distance. And this is the x-axis shows time. So today is at 0, and this is backwards in time. So this is 10 billion years, 14 billion years, and so on. And this is forwards in time. Now the way this has been plotted is that the cold region, this region over here, is what you would expect if the universe were decelerating. If the universe were going as expected, going slower and slower and slower with time. The blue region is if the universe were accelerating, if it were going faster with time. And what you can see is, these are the measured points. What you can see is that all the points are sitting in this blue region. All the distances are higher than you would expect if the universe were decelerating. And that's actual data over here. There are about 100 points at high redshift larger than about 1 today, or 0.7 or so today. So there are about 250 points in this plot right now. Most of which are here, about 100 are here. And every single one of the points is sitting in the blue region, which says that over the last 7 or 8 billion years, the universe has been accelerating under the influence of this dark energy. And from this, and the cosmic microwave background, you can show that 70% of the energy density in the universe is in dark energy. And I should mention that the Nobel Prize in 2011 was given to Alan Rees, Saul Perlmutter, and Brian Schmidt for this work in the late 90s. So this is the only evidence for this dark energy, for repulsive gravity, is coming from cosmology. We have no evidence from this for this kind of energy in the lab today. This is completely astronomical. It's astronomical in surprise and it's astronomical in observations. You want to do this? And then close the last.
最后呢，大概2年前的诺贝尔奖，就是这个稍微解释一下，这是一种特殊的天体，这种天体它是一个双星，它质量没有到那个临界线，它就不会爆发；一到临界线它就爆发。可是到临界线爆发呢，它爆发的那个亮度就是固定的。既然有固定，它就可以当做标准烛光。那因为它爆发很亮，那种超新星，所以它可以看到很远，可以看到1.2。所以利用这个标准烛光拿来测，拿来画哈勃定律的话，你就可以测很久以前的宇宙膨胀的情形。那长话短说，就是以前的宇宙没有膨胀这么快，那表示现在的宇宙膨胀比以前快，那宇宙在加速膨胀。那加速膨胀就很奇怪了，任何一个膨胀的东西，因为外流引力总是要减速的啦，那没办法解释这件事情，好像有一个反重力的事情，现在还不太懂，实验室完全没有这种东西，只有在宇宙里面看到这种东西，完全不懂，所以就把它给一个名词叫做暗能量。所以暗物质跟暗能量是完全不一样的东西。暗只是表示我们不懂，暗物质一定存在，可是我们不知道它的性质。暗能量还可能不存在，但是它展现出来。Next one please。现在我们的证据发现，宇宙中间有5%的你我这种正常的物质，25%的暗物质，70%的暗能量。这目前我们知道的宇宙的物质的能力。
Thank you. 25% of the energy density of the universe is dark matter, non-baryonic dark matter. 70% is dark energy. What's left? 5%. 5% is us, baryons. That's the picture that we have today. This is the best cosmological model today, what is called the lambda. Lambda because lambda is the term for dark energy, for the cosmological constant. The lambda cold dark matter cosmological model. Cold because the dark matter is believed to be non-relativistic. And that comes from this wonderful fit to microwave background data. And that gives us baryonic matter contains 4.9% of the universe. Non-baryonic dark matter contains about 27% of the universe, and dark energy contains about 68% of the universe today. That's what we think the universe is like today. So where do we go from here? It's cosmology over. We have all these wonderfully accurate answers. There are big questions that still remain. A big prediction in cosmology is something called inflation, which happened at extremely early times in the particle physics epoch. So one of the massive predictions from inflation is that you should expect to see gravitational waves, ripples in space-time oscillating out from the inflationary epoch. And this can be measured again from the microwave background. And this is wonderfully difficult to do and wonderfully precise. The second thing, which is huge and which is really the place where I think a lot of us are going to be struggling in the next 10 or 20 years, and I hope that some of you will be struggling as well in it, is what is the nature of dark energy? What exactly is this dark energy? And there are lots of experiments being done for this. An example of a great experiment is weak lensing, where you use gravitational lensing of background objects to probe the evolution of structure in the universe and try to probe dark energy. There's something called baryon acoustic oscillations, where you do similar things. I won't go into details of either of these. The next thing you can do is that you can measure the masses of these high redshift galaxies as a function of distance, of redshift, and probe the cosmological model. And since, most of you, all of you are in school, and I hope that at least some of you will become cosmologists, the big thing in science and astronomy today is really big telescopes. You can do wonderful astronomy if you have access, if you can observe with great telescopes. And something that I'd love to tell you is that in Taiwan, which is a small country, it's not a huge country, astronomers in Taiwan have access to the best telescopes in the world. These just show two of the great telescopes. Subaru is quite old right now, it's about 10 years or so old, 10, 12 years old. And Taiwanese astronomers have access to Subaru. One of the great experiments happening right now with Subaru, just started last year, is this wonderful camera called Hyper-Supreme Cam, which is the biggest field of view of a camera on any big telescope. It's 1.5 degrees on the sky, 3 times the size of the sun. And using Subaru, which is an 8-meter telescope in Hawaii, and this wonderful camera, you can probe weak lensing. You can also measure type 1a supernovae. And that's one of the great projects which will happen over the next 5 to 7 years, which people in Taiwan are heavily involved in. Another spectacular telescope, this is one of the greatest sites in the planet for astronomy. This is the Atacama Large Millimeter Array. It's sitting at 5,100 meters in the Atacama Desert in Chile, high above sea level, and it's just coming online right now. It's going to have 50 of these antennas when it's fully built, about a year from now. There are already 37 antennas there, and it's already producing wonderful science. And this telescope, ALMA, will actually measure high redshift galaxy masses to ridiculously good accuracy and ridiculously large number. Again, Taiwanese astronomers have access to this telescope. And this telescope is truly outstanding. It has no competition in the world. Subaru there are other big telescopes like the Keck telescope and the VLT, and there are new telescopes being built. ALMA is just wonderful. There is nothing that competes with ALMA at its wavelengths. It's a path-break telescope, and I'm happy to tell you that Taiwanese astronomers can use ALMA. So, do astronomy, use ALMA, do great science. So I'm going to summarize here. If there's one thing I want you to take away from this talk, there will be 2 things. It's that the universe is expanding. If you're telling your mom or your dad about the universe, tell them that. We know that the universe is expanding. And even more exciting, we know that that the expansion is accelerating today. These are the 2 fundamental facts of the universe. Just from the acceleration, we know there must be dark energy. So if you just tell people this, that kind of summarizes the universe for them. It's expanding, the expansion is accelerating. We believe that the Big Bang cosmological model of a homogeneous isotropic universe in early times, evolving into today's universe full of stars and galaxies, is the model that describes the universe. And the two big pillars, the two big pieces of evidence for this are nucleosynthesis predictions for deuterium, helium, lithium, which match the observations wonderfully well, and the microwave background. Spectacular evidence of homogeneity and isotropy, 1 part in 10,000 at early times, and those tiny little CMB anisotropies which grow into today's galaxies. The galaxies form by small growth of these tiny inhomogeneities, these tiny overdensities because of the laws of gravitational attraction. 70% of the energy density of the universe today is dark energy, which we know nothing about, and which is going to be an active area of research in the next few decades. And finally, the Big Bang lambda CDM model gives an outstanding fit to current data. And there are still open questions: nature of dark energy, when did the galaxies form? So cosmology will continue to be an active field, certainly for the foreseeable future, certainly in the next few decades. Thank you.
All right, open to questions. 有没有什么问题啊 ？Okay, can you pass the microphone?
I want to ask that the huge structure of the universe is inhomogeneous. Is because of the inhomogeneous of the dark energy?
No, that's a good question. Dark energy seems to be very homogeneous. Dark energy seems to be quite uniform. And that's, you can kind of understand, you can see that immediately, because if dark energy were not uniform, then the expansion will be different in different directions. Right? But you see the expansion is the same in all directions. The acceleration is the same. So that's telling you dark energy is very uniform. Baryons and dark matter are not uniform. So baryons and dark matter cluster because gravity is attractive. But dark energy is repulsive, so it doesn't cluster. It actually pushes things away. So based on looking out, we can see that there's no evidence that the dark energy clusters. So therefore, it's very hard to detect dark energy. That's a very good question.
好的问题就是说，暗能量会不会是不均匀的？目前猜想大概暗能量是蛮均匀的，因为这个推的力量让宇宙的膨胀在各个方向是差不多的。可是物质跟暗物质好像是不均匀，因为它们是有万有引力作用，万有引力会让密的越密，疏的越疏。非常棒。Okay, we can get one more. I think we have to close it somehow. Okay.
Two more.
Two more.
Good. Exactly two more of these left over.
Oh, wonderful. Okay.
I have a question about redshifting. The delta frequency of the light of the light is always is the same, because in the picture the angle of the redshifting is all the same.
Sorry, I couldn't hear you.
I mean the radiation frequency of the delta of the radiation frequency, the redshift.
Right.
Yeah, it are always same in different
of the microwave background? Of what? The redshifts of
Of
galaxies?
The difference of the redshifting. If the speed or the distance are all in the same condition, then
I'm not getting the question.
要不要试试用中文讲？
就是那个频率的差别，
是什么感？什么频率？
就是同移的时候频率的差别就是在如果其他状况都一样的话，在不同的频率光在的那个同移的频率差别是一样的。
Okay. Yeah, he asked a basic question. Whether the redshift will be the same at all frequencies.
Yes. Yeah. So in fact, that you can see.
So there's one figure.
Yes. Yeah. So here you can see that these are different frequencies, different wavelengths. That's high frequency, this is low frequency. All of these lines are shifted by the same amount. So the redshift is the same at all frequencies. Definitely.
thank you.
同移就是很有意思，它是整个平移。
The whole spectrum shifts.
It is possible that an expanding of the universe is faster than light.
That's a good question, and it's an interesting question. But that connects to this. So suppose the velocity is equal to c times z. Right? So in the limit, suppose z is 1, then the velocity is equal to c. If z is larger than 1, it seems as though the velocity is larger than c. And that seems to be a problem. And that's the reason one should be very careful about velocity. Velocity is not the right way to think about the expansion. What's happening is not that this galaxy is moving. What's happening is that space is stretching. This space is pulling apart. So there's no problem with special relativity. Special relativity tells you that you can't go faster than the speed of light, right? So you can't move, an object cannot move, the mass becomes infinite, 0, at the speed of light. So you'd have to have a 0 rest mass particle to travel the speed of light, and you can't go faster than that. That's the exact reason that this picture is showing that this galaxy, so it's not that this galaxy is fixed and that galaxy is moving. What's happening is that both galaxies are fixed and space between them is stretching. And so it looks as though this galaxy is moving with a high velocity. It's not moving with a high velocity. Space is stretching. So this picture is important. It's not due to physical motion of the galaxies. So there's no problem with special relativity. Special relativity is about motion, kinematic motion. This is about the stretching of space. So the picture that you have for the universe has to be very different from special relativity. Special relativity only applies on small scales, galaxies or nearby galaxies, not on cosmological scales. But that's a very good question. Wow, sorry. Nice goal, which was.
好，我想我们今天就把宇宙从头到尾交代了一遍。好，谢谢大家，我们谢谢讲者好吗？